Good evening, sir.
Sir, good evening. Sir, we'll be waiting few more minutes.
आपको किसी ने 10 टाइम मारे होंगे मुझे पता चल जाएगा बताइए इतना इसने मारा इतना इसने मारा हाँ यार वही वो पूछ रही थी बोल रही थी मेरे से चिढ़ती है वो किस
था नहीं।
देखो नहीं, I wanted. Shomrit sir, are you talking to us? Like your voice is not coming properly.
Okay, am I audible now?
Yes,
এখন
sir.
শোনা
Now,
যাচ্ছে?
হ্যাঁ হ্যাঁ শোনা যাচ্ছে. Sir, we
Okay,
are waiting for a few more minutes. Then we'll start at
no
around
problem.
6:05, sir.
No problem, no problem.
Okay, okay,
Yeah,
okay, okay.
thank
Thank
you.
you, sir. I think Kamalesh sir and Shorav sir, we can start, right? Because it's almost
Yes,
6:05.
Yes,
6:05.
ma'am.
Okay.
Sure, ma'am.
yes.
So almost 119 participants have joined and sir has already joined. So we can start today's session. Um, a very good evening, dear participants and respected speaker. Today is our second day and we are about to start our session. Hope you have enjoyed a lot yesterday. There were a few issues in yesterday's sessions, especially it's for them who haven't logged in or submitted their feedback with their registered mail ID. So it's a kind request from our side. Please log in with your registered mail ID along with please submit the feedback after every session with your registered mail ID and please complete the registration process within 12 a.m. every day. This is because next day whenever we are compiling the attendance, you know that there are huge number of participants we have in this FDP. So every day like managing like different mail IDs is basically a troublesome job for us. So please do cooperate everyone. uh, and the second issue is like today you are being made as attendee because yesterday you have seen there are so many noise like for smooth conduction of the events or the sessions. Basically you are all being made as attendee, so unnecessarily do not unmute yourself because it will create a problem with the speaker. If you are having anything to share, you can raise your hand. Definitely we'll take care of that. Or after some time, I will open the WhatsApp group for everyone. So at that time, you can ask your queries over there. We can share with that, or we can unmute yourself. We will unmute you so that you can ask your queries in the question answer session with sir. Okay, so let's start without any further delay. Let's start a brief introduction of sir. Mm, so it is a great honor to introduce our esteemed speaker, Mr. Shomrit Kumar Maiti. Basically, sir will be delivering the next two sessions of day two of the FDP on emergence of cloud computing, cloud technologies, and recent trends. Shomrit Kumar Maiti, Scientist E, HPC Technologies, CDAC, Pune, is associated with CDAC from 2006. As a part of National Supercomputing Mission, he is involved into porting, benchmarking, and technical support of scientific applications with his expertise on high performance computing, deep learning, machine learning, parallel distributed computing, and accelerator computing. He leads the team responsible for strategize, implement, execute, support deep learning, machine learning applications stack on supercomputing systems under National Supercomputing Mission. His team looks after Param Shavak DL GPU and Param Shavak VR product development and deployment. His area of interest includes high performance computing, distributed deep learning, machine learning, heterogeneous computing, accelerator programming, grid computing, system administration, and big data. So over to you, sir. We are eager to hear from you or to get some knowledge from your part. So, sir, over to you.
Thank you very much, madam. Hope I'm audible.
Yes, sir.
Okay. A very good evening to all of you, and thank you very much for the opportunity given. This is after a long time I'm delivering a talk on high performance computing to the eastern part of India. So it's a privilege, it's an honor, and I do hope my sessions is going to be beneficial to some of the attendees. I will try to share my presentations now. Kindly help if any technical glitches comes up. Okay. Is it visible?
Yes, sir, it's visible.
All right. So, all right. So, when the proposal came for these presentations, FDP session, I was thinking what to talk on. I could have selected many other topics. However, I always preferred the core topic that I've been investing a lot of time behind for a very, very long time. So, by the way, if there is audio problem or if you are not able to hear, kindly stop me so that we can resolve those issues. Yeah. So then I thought that I would start from the beginning, and I'll be talking about the basic stuffs, and I would make the presentations more informative. And I have few disclaimer as well to tell you that this particular presentation is informative presentation, so it is not a scientific revelation, so to say. Though my designation says I'm scientist E, but technically I do tell people that we are basically technologists. We do enable technology to the people, to the end users who are the scientists working on HPC systems. So from that perspective, as it is very near to my heart, my favorite topic, high performance computing, I'm getting a chance to explore and go along through the journey of high performance computing from the basic onward. And then, I'm actually starting from very beginning, as if like myself is learning the topic, myself has learned the topic as well in same fashion. For a very long time, I've been invested my time into system administrations, and that too supercomputing building. So I know a lot of details about how different components are organized, architected, and then placed together in order to make our supercomputing systems work smoothly. That's why I thought possibly this is one of the topics that I can talk on, and as there may be very very respected scientists in other sessions who will be talking about science. So this is about technology. This is the first disclaimer for my session. Yeah. So it's a total 3-hour session. There is a possibility that you may get bored, and then I would try my best to make it enjoyable. But yes, I understand total 3-hour session, and then you are continuously consuming informations that I am trying to tell you may become little bit bored sometime, and that's why we'd go phase wise. We'd take one particular sections of explanations one at a time, and then we'll take little bit of break, and I'll go slow as well, because it may happen that you may have some questions or queries in between. I do hope that this particular technology talk, or this particular kind of technology talk, as a computer fraternity, you may not have gone through before, but there is a possibility that some of you, I think almost 130 people now, are joining this session. So some of you may have already gone through this session and these kind of sessions before. I'll be talking about technology first, that why we are talking about high performance computing, and I'll be talking about, and then I'll be telling you about the detail of the ecosystems. High performance computing systems and the whole ecosystems is not a single domain work. Frankly speaking, multiple domains and I'll be talking about all those domains. Scientific domains are there, technological domains are there, engineering domains are there. All are coming together to make our data centers, which is a kind of a supercomputing infrastructure, working smoothly, and then the end users will be using it. So there is a lot of ecosystem related challenges. I would try to highlight them. And then there is practice. So when I started my journey, I always used to wonder that in our college days, in our graduations or a master's time, we never encountered anything beyond the desktop system. That was the time of that kind. Mobile computing was not available. So we always thought, okay, desktop system is the end. I mean, beyond it, it is a distributed computing domain and which we do not have much access to. So we could never explore, exploit, experiment with anything of that kind, so to say, distributed computing systems. But very coincidentally, I do not know why, but very coincidentally, when I was doing my graduation, the first computing language that I learned was Fortran. And then I never knew that one day it is going to be the most prominent, useful thing for me. I never knew that almost 20 years back. So I was learning Fortran, and then C language was becoming very popular, and then people were learning. Most of the people were very excited about C, but somehow I could stumble upon Fortran language, and I took up that. And then later on, I moved to C language. So that was a kind of a coincidence. Latter point of a time when I actually got employed onto a thing called supercomputing platforms and domains, I saw that most of the applications, scientific applications, are written in Fortran. It became very, very easy for me to do a lot of stuff around. So when I say practices, I simply means that it is not um, it is not a normal learning process that you go through in your engineering degrees, in your graduations. It is a bit different. Though the basic ingredients, basic styles are same, but working on a distributed computing systems requires a lot of different kind of knowledge, and you need to apply them in practical in order to reach to the solutions. And many of the cases, it's frustrating. So you have to overcome those frustrating situations. Then you would get to understand, okay, this is the reason I'm getting these challenges. And that becomes learning. It's very difficult, many cases, to transfer this knowledge from one person to another. And that is one of the primary challenges that we face in HPC. The resources are very scarce. We find very less number of people to be employed directly on technological domain like supercomputing applications. Well, again, here is a cross domain connections. The applications, the end users of supercomputers belongs to scientific domains: astrophysics, computational chemistry, physics, computational physics, mathematics domains, biologists, and whatnot. Nowadays, AI people, then quantum simulators, the people who are doing quantum simulations, they are the end users for these applications. They know why these particular calculations and formula been there. Now, as a computer person, it is very difficult to understand them. So you require patience to collaborate with them, understanding their problem, how they have transformed their formula into programming languages and algorithms, and then how those algorithms are working, why they are taking too much of time, why they fail, why they perform in case, all these things. So it's always a collaborative environment, cross domains, people's collaborations and work in order to make the output fruitful and useful. And there are a lot of challenges, you see. As a computer science person, you do not understand the domain much. Let's say it's biology, so you don't understand too much of biology and why a particular scientific computing model is designed in this particular fashion. Whereas, on the other hand, the domain people do not understand computer science much. They have little bit penetrations. Nowadays, the orientation sessions are there. So many of them are going through it. So they know a little bit of it. But when it comes to, accelerating, scaling, optimizing, making it better, redesigning the applications, it's always limited scope. And that is why there are a lot of opportunities, challenges. Challenges and opportunities come hand in hand. And a lot of in-depth core scientific knowledges are also required in order to solve those problems. Here is the warning and disclaimers from my side. I always love to give this disclaimer because I know we are coming from different background and we may not be appreciating all kind of informations that are going to be shared in every sessions. So in my sessions, it's a 3-hour long sessions. It may get bore. And also I have a very kind of, I don't call it bad habit or good habit, but I have a habit of simplifying things. That is how my brain works. I co-associate, co-relate concepts, and then I do love to present them in a story form. That may become a little bit, otherwise not so interesting for some people who are looking for hardcore scientific ideas and problems. My presentations is basically going to be a story form, simple story form. And as I said, we'll break it into phase-wise form and then we'll go into question and answers if possible. So do ask questions if you are finding it interesting. I would really appreciate them. Though in the first phase, let me tell you the phases because it is very important. There are almost 150 slides and I'm going to talk about everything, the complete ecosystems about it. I'm going to talk about civil, I'm going to talk about power management of a HPC system, I'm going to talk about how system administration is done, how it is designed, the coding part of it, the complete data center part of it. I'm going to touch upon almost all areas. So if that is the case, you understand that it is again a cross domain thing. And that's the reason that I have broken it up into phase-wise fashion. And I will sometimes come back and tell that here we are standing. That means when we are in the sections, introduction sections, we'll be talking about the introductions, and maybe I will be reminding you multiple times that this is the introduction session. And then we will look into the hardware scenarios. What are the different plethora of technologies, hardware technologies are there in order to make computing systems as a high performance computing system. A lot of softwares and their methodologies, their programming patterns, their design patterns, I'll be discussing in the third phase. Little bit of system administrations because it's a practical field. I would not be able to cover everything within 3 hours, but yeah, little bit of it, how it works, that I'll be talking about.
Excuse me, sir. Excuse me, sir.
Yes.
Sir, a few participants are telling that your voice is coming low. Maybe it's the problem from the participants or like just.
Yeah, I'm trying to be loud, and that is why I've kept the mic.
Okay, sir. Okay, sir. Please carry on, don't mind.
Okay. Yeah. So this is the overall roadmap of my presentations, and let us start with introductions. On the right hand side, the picture that you are looking at is a glorified picture of a supercomputer. We normally call it as a HPC, high performance computing system, but let's not get overwhelmed. It is just an aggregation of multiple computing systems together, and by some mechanisms, middleware, system software, algorithms, applications, and people. They are all together and making, creating a picture, creating an illusion that this is a monolithic, humongous, big computing system. It is not. It is basically a collection of many number of computing nodes, like your desktops. That is why it's called COW, COW, collection of workstations. Sometimes it is called. These are not collections of workstations. They are very high-end server class processing systems. But yes, there can be thousands of such processors, and the picture may be a little bit over glorified, but in reality it looks like this. The test systems and things like that, lot of wires, lot of connections, and there is a storage, there is a network component, there is a computing part of it, computing unit, there is a display sections, display visualization servers, cooling unit. The cooling unit is not shown here, that is a part of the data centers. So all things becomes a big computing racks, a collection of racks, where even the power backups would be, which is basically like a series of batteries are placed. So all these are placed rack after rack. That is how it looks like this. It is not a mainstream subject. Till now, I am considering this way, but you may argue with me, you may debate with me, and you may possibly be right, and that nowadays it is people are becoming aware of it. Thanks to something called cloud computing, I started my career with grid computing in 2007, 6 and 7, and I knew that time the cloud domain was just appearing slowly. 2009, it just picked up, and and grid computing was slowly diminishing. During that time, I knew that cloud computing is going to be big. And because of cloud computing, nowadays, most of the people are aware about something called distributed computing platforms, thanks to cloud computing. However, HPC is one such distributed computing platform, which is in many cases co-located. That means it is tightly coupled, placed at a single place, single room in many cases, and with monolithic kind of a set of architectures, etc. So this is another category of a distributed computing system. It is not popular. If I say it is not popular, it's somehow wrong, because scientists across different domains, day-to-day basis, they use it. And scientific simulations is the fourth vertical of exploration. I'll be talking about that scientific simulations a lot. So I'm saying it is not popular because on day-to-day basis, in engineering domain, in basic science domains, we do not use these systems. Once we move to higher studies, we get in touch with HPC systems, because that becomes one of the necessary thing in order to do simulations and explore scientific explorations. So that is one reason, but there is another social reason, which is related to the employment. India, as a populations and an engineering community, oh, there is a lot of interest to provide services, because services has money. It is not related to core scientific exploration. Services, in services domain, we do develop, design, discover, and innovate lot of tools and technologies in order to make end users' lives easy, and that picked up in last 20 15 years. That actually went very well, and that is how there is so much of good images of computer science, computer technologies across, because it generates a lot of employment. However, uh, because of that reason only, there was not much emphasis on core development of computer related technologies, specifically investment behind distributed computing. When I say investment behind, I'm not saying that you as a individual don't want to invest. Possibly you are very much interested to work upon, but there is also not much push from the decision makers, the policy makers, to invest something related to the computer middleware. And that is why you see in India, we have not developed an operating system of our own. We have not developed a middleware software of our own. We have participated into the development through open source activities, but till now, those activities are very limited, and there is not much push into developing something of that sort because of this reason. The scenarios are changing. people are realizing, the decision makers, the policy makers are realizing that there is a need to be independent in terms of applications, in terms of middleware, in terms of hardware. There is a need, and that there is always encouragement into every stack of computer systems. Stack, when I say every layers of computer systems, that means there should be sufficient and interesting work should be going on the middleware development, like runtime development, programming language development. India haven't developed programming languages also. There is a lot of activities going on across IITs, ISCs. There many researchers has developed languages also, but they have never become commonplace because the project possibly not funded for a longer period of a time and all that case. That is possibly another reason that we don't know much about supercomputing. So this picture is talking about very, very serious stuff. In 2010, if you look into China, there was like 25, not even 25, less than 25 supercomputing systems, China. And they realized to sustain the scientific growth and to reach beyond their capacities, current capacities, they have to invest behind something called HPC. And they started very, very aggressively. We used to talk about it in 2011, 2012 time. And in 2015 to 19 period of a time, China became within this kind of 9 years time, they become the leading supercomputing nation in the world, because they realized one thing for sure: if there has to be path-breaking scientific explorations, there has to be supported by HPC, because HPC is the scientific simulations platform, the technology. It is like a microscope. If you don't have a microscope, you cannot do microscopic explorations, and you cannot do any basic scientific explorations in biology. So in a similar fashions, HPC becomes of similar tool, and China realized that. They started investing heavily behind it, and current point of a time, it is competing with US. Maximum number of, in many cases, maximum number of supercomputing platform China has. And they not only investing behind the HPC platform, they are investing for creating their own hardware, the processors, the motherboard, the all kind of drivers, operating systems of their own. They are actually at this point of a time, they are investing heavily, and they have came up with their own accelerators. Right now, across the world, NVIDIA accelerators as the prime candidate for accelerations of computations, but China has their own. So, because they understand at a certain point of a time that if they want to go beyond and want to be a developed nations, they have to invest behind. Why I'm talking about it? Look at the last year. This is South Korea and India somewhere. I'll show another picture. In this, somewhere India is. So I'm not proposing that India should very aggressively invest, because every country has their capability and also priorities. So, but to make things break, to bring out a lot of breakthrough outcomes, scientific outcomes, either today or tomorrow, India has to take that decisions. And frankly speaking, India took that decision with the NSM, National Supercomputing Missions. I'll be talking about it a little bit. Here you can see this is a very recent statistic investment behind HPC, and there is a platform called Top 500, which lists top 500 supercomputers across the world. And you could see India has almost 1.2% contributions in the number of supercomputers across. Whereas here is China, 12%, and the United States leading with 34%. Now remember that if you look in this particular timeline, which is around 2015, China was biggest. They invested a lot. Again, their competition started, and United States actually catches up with the competitions. And right now, because of NVIDIA and many other things, it is growing. They are at the leading position. This graph actually tells how countries are investing, but it has distance correlations with how scientific community of the country, of the respective country, is getting the chances to do scientific simulations on compute platform like HPC. This is very important because the more number of scientific simulations are done by the domain scientist, the more breakthrough possibilities are there. Okay, this is about the investment. On the left hand side, you see this talks about what is the operating systems that a supercomputer runs on. And you see, it is a single color. Always it's Linux. Earlier, before 2007, there were few exposures of other operating systems like Unix, but Windows, it was never. One or two systems came up with, but that was too experimental that time. Right now, it is completely dominated by Linux. So if this is what the message to whoever is attending these sessions, if you want to be good at distributed computing, you have to invest a lot of time to learn Linux operating system. As I said, Government of India has launched National Supercomputing Mission, and the primary objective was to deploy 72 world-class supercomputing platforms across premier institutes. And CDAC, being one of the nodal agency, took the lead role of deploying those supercomputers. And another nodal agency was IISc, who was leading on the application developments also, and also many other aspects of supercomputing building, especially the core R&D part of it. So right now we have almost deployed 33 of these, 33 supercomputers. And another major important factor when this mandate of national mission given to CDAG and IISc, one of the primary responsibility was that Atmanirbhar Bharat. Under Atmanirbhar Bharat, it was planned, mandated, and given the task that you would be developing your own indigenous hardware platforms. And under that, we came up with something called Rudra, Param Rudra platform, a server platform. So this is completely indigenous. And the good news is the phase 3 machines, supercomputing platforms, are completely Param Rudra based systems. I'm not talking about the processor. Processor is still coming from Intel or AMD. However, a lot of work going on around on the processor part. Very soon we'll be coming up with a HPC processor. We are investing a lot of R&D efforts behind it. But at this point of time, Rudra is a platform, server platform. So you can say it's a motherboard on top of which the processor sits. So based on this platform, we are building the phase 3 systems, and these are phase 1 systems, IIT VHU, ISR Pune, and then there was a systems in there is a systems in IIT Kharagpur as well, Param Shakti, one of the largest phase 1 system, Param Shakti, located at IIT Kharagpur. It's very much in use by Kharagpur itself, also the outsider participants. So I was talking about the phase 3 systems. So we have already deployed 3 of them. One is IUSC, Delhi, and another is GMRT NCRA. They do a lot of astrophysics related work, R&D. IUSC do national strategy wise, I would not be talking about. SN Bose, this is in Kolkata, very recently been inaugurated, and SN Bose systems called Param Bosan. So this particular, all these three systems were inaugurated by our Honorable Prime Minister, Sri Narendra Modi ji. So phase 3 systems are all getting deployed with a platform called Rudra, Param Rudra. It can host a 2 Intel GPU, Intel Xeon class processors, which is having total 48 cores, dual socket. The picture that you are looking at is a 2 GPU platform. It's a 2U form factor, Whereas the normal CPU core systems Rudra platform is 1U, which is much thinner. So this one with GPUs, and this is also successfully delivered for building the systems. Why we should be little bit proud and excited about HPC is this: lot of path-breaking scientific explorations are done on HPC platform, and here is two recent example. One is from 2024, another is 2023. Nobel Prize winning work has been done, explored research has been done and supported by HPC platforms. You can search on internet. Many other path-breaking research work is going on around spatial astrophysics and bioinformatics, like drug discovery applications. Those applications runs on HPC platforms. So we have concluded the very basic introductions of HPC, and I have talked about national initiatives that are going on by this time, and now we'll be getting into slowly. So I have talked about what HPC is. I'll be giving you historical perspective after some time, but right now let us get into why we require HPC. Okay, so before getting into there, why we require HPC, we have just concluded introductory part of it. Is there any question? I will take a pause, maybe 1 minute, and then I will move to the next phase of presentation, that's especially on scientific simulations. Is there any questions by this time? Okay, I suppose there is no question. Let us move forward. So scientific simulations is basically a science to create simulations models, simulated models. So if you look into the right side picture, we have real systems or real life phenomena going on. By looking at it, we do objective scientific explorations. There is another form of exploration, scientific exploration, which we call as a subjective scientific exploration, so where we employ ourselves for the explorations itself. Many people call it, let's say, to give it just correlation, it's a kind of a meditations, so where you yourself is the tool, you yourself is experimenting some new ideas, and you yourself is going to realize the output. You may tell it later point of a time in form of writings, in form of books, but basically you are the explorer, you are the tool and technology, and you are the realizer as well. So this is the first kind of an exploration. So whereas objective exploration, scientific exploration is the other kind, which is very popular, rationally correct, seems to be, in modern day. Where what we do ideations. We think about something, and then question arises, and we get some ideas out of it. How to explore and find out whether my idea is correct or not. So how it comes, because we are observing some real life event. So real phenomena, once we observe, some questions will arise. Based on that, we'll be having a lot of questions and queries, confusions. Then we'll be developing tools and technologies. We may inherit some of the knowledge by reading research papers, but we'll be basically having our own unique ideas to move forward to the next stage. That means we'll be making a model, simulations model, and then that is how the right side picture is talking about. We'll perform some experiment and we'll get some experimental results. Once we get experimental results, we may also give our ideas to model in case of scientific simulations. That through that model we will be getting simulated result. Here it is. Okay. Now we can verify the experimental results with simulated results, and we can compare them in order to understand how much my idea is valid. Also, out of simulations and things, we may create a theoretical predictions as well. So these three pillars of explorations goes hand in hand, validate each others. You see here, validate each others, or rather, I would say, helps to validate each others. That is how scientific simulations becomes another pillar and support mechanisms for scientific explorations. It is also very much necessary and important and interesting because it costs less. You do not have to actually play around with real instruments, which may become very costly. You can do a lot of simulations and zoom in, discard lot of false ideas, and then zoom into more correct, more probably correct ideas, and then you can really experiment with those ideas. That means on computer systems only you are discarding a lot of possibilities, and that is how you are saving a lot of money. In real world also we do the same thing. If you look at mathematics is also a similar kind of tool. What we do in mathematics, suppose we have a real world component or things, an object, and then we associate some numbers, mathematical numbers with it. Suppose I have two chocolates, I will give a symbol called 2, and I will associate that with that number. Okay, something like this. Okay, so here what we are doing, we are simply associating some abstract symbols with real object. Once we are doing that, it gives us immense capability to do the calculations. We don't call it as a simulations, but we call it calculations. And suppose we have a problem that I have a 10 box of chocolate. Each box has 5 chocolate, and then how many chocolates we have? First of all, even if we don't count, we would be able to calculate we have 50 chocolates. And then if I say how many amongst how many students I can distribute it, I can do it on pen and paper without doing it on reality. Yes, so this is a form of simulation going on. It is happening in the form of calculations on pen and paper, but this is also a form of simulations. The outcome is fantastic because you don't have to practically do it. You are simply doing it on pen and paper, and this is actually the basis of simulations. If you look at, this is the actual basis of scientific simulations also, because there will be a lot of formulas which is residing inside mathematical models, and those formulas are basically will evolve with more and more data, more and more calculations, and that is how a scientific model would give you the final output, right? At this point of a time, computational physics, astrophysics, climatology, chemistry, biology, manufacturing, they are the primary users of scientific simulations. But latest entry is artificial intelligence. Artificial intelligence is also becoming part of and somehow converging with HPC domain because it also helps to realize some of the output in a very fast way. So instead of doing the real simulation stage wise one after another, the traditional computational method, it can bypass those computations. That is how it saves a lot of computational cycle, and that is why people are liking it too much. So simulations as a science started to get developed during World War II. There was a lot of competitions between Russia and US for space science, nuclear physics, and many other technological fight was going on between these two countries. And one of them wanted to overpower with the others, and that leads to a lot of rapid development of a lot of scientific technologies, but that was also gave the rise and shows the prominence of scientific simulations, because if you want to produce something, productize something very fast, you have to quickly simulate a lot of things, the way a vaccine simulations works, medicine simulations work. So these are the prominent areas, but yes, lately a lot of other domains are slowly making its entries. One of them is like artificial intelligence, another is sociology. During the COVID time, you must have heard that social experimentations was going on. Lot of calculations, machine learning models, people brought up in order to tell that after 1 year how many people will be infected with. This is also a kind of simulations. Also, there was other kind of traditional simulations happened on HPC systems, and that was related to drug discovery. And that is why, if you remember, there was a news came up on newspaper that US dedicated all of the supercomputing facilities for drug discovery and vaccine discovery related work. During COVID time, they actually stopped all other scientific work, and it was only given to the bioinformatics people, biologists, so that they could have a dedicated access to the systems and they could do a lot of simulations. Weather forecasting is one prominent candidate and which has direct impact socially. If you remember early days, 2020, 2001, 2002, the weather forecasting's predictions were not too correct, and nowadays it is it is too correct actually. In many cases, it helps to save lives, and it is very much socially impactful applications. How it is becoming that way, I have not put those slides here, but there is a department, Indian Meteorological Department. They are responsible for simulating weather, and they have a lot of weather forecasting models. They have developed them. Also, a lot of weather forecasting model they have their own, as well as open source model. Along with open source model, these models they run day and night to analyze and forecast weather, and that is how, in case of typhoon, in case of tornado, in case of any natural calamities of nature related calamities, they could predict and forecast at early stage, which helps the decision makers to take decisions and take corrective actions. In case of recent, many of such event, especially Odisha government has taken the most effective approaches. They have actually lined up with these decision making, policy making methods. They have lined up national disaster management as well. So once you forecast something is going to happen, immediately all other machineries, government machineries will get activated. They have a protocol actually, and then they will automatically plan by their own. And that is how you see in recent time, Odisha, the human life loss because of tornado or such national calamities is very, very less, thanks to governmental initiatives. Um, so technically, you may call it as a visualization technique, but it is actually not. There is a scientific model working behind, which is completely rationally based on science, and they do a lot of calculations. After that, phase wise, they evolve that model, and one boundary conditions to another boundary conditions it reaches to tell people what is the whole systems, what is going to be the final state of the whole system. And that is how they produce the lot of data in between, intermediary data as well as final data. Once you process those final data using appropriate tool, you can visualize them for the decision making purposes. Inferencing is a one of the very important part of it, the whole pipeline, but it is the last stage of it. The primary condition is you should have good feedback input. If you have a good input, then your model will evolve correctly. Suppose you have a liquid, and inside the liquid you have given one new molecule, you have just put in one molecule. Now there will be a lot of reactions going on inside those billions of molecules. They will be interacting with each other. This is called n-body simulations, and you don't know, you want to simulate them to the fraction of seconds, because you want to capture them what is happening around in order to understand that scientific phenomena. And for that particular purpose, you require a humongous computational capabilities. How it is simply done, you basically discretize a continuous phenomena which happens in reality, cannot be simulated because it is too compute intensive even today, and that is why I may go a little bit out of the scope, but yeah, that is the reason quantum computing is coming up, because quantum computing can simulate quantum event, which is the real events in a quantum systems. Whereas on HPC systems, it is always discretized by discrete algorithms, mathematics. Okay, once you discretize something, you are going into the form of approximations. That means you are losing some form of information and you are capturing some form of reality. So this is called sampling. So some form of reality you are able to capture, whereas some form of you have to approximate. Whenever you go into the domain of approximations, you know in mathematics, in any form of approximations will never be equals to the reality, whereas it will be near or close to realities. That depends on how much computation capacity you have, and that is why whatever model, and here is the reason, even the weather forecasting model, they are so humongous, so big, computing systems are behind day and night. A lot of engineers, scientists are working behind. Even after that, they fail because it is an approximations. It is not the reality that you are actually calculating upon. It is some form of approximations. Now let us look into what are the different form of scientific simulations are available. You could create a simulations like wind tunnel in order to simulate a turbulence for a plane when it is flying. So this is called real simulations. You have a big instruments, a wind tunnel, and then inside that you are creating a lot of air force, and that air force is your model, your flight model is placed inside. It is going through it. A lot of IoT devices are collecting data when you are actually flowing the air inside or through the wind tunnel. This is a form of simulations, but this is very expensive because to build such a tunnel, you have to invest a lot of money. There is an alternative, which is normally done. Computational fluid dynamics, a very, very prominent domain in scientific simulations. And these simulations and things works on a supercomputer. So these two different approaches are not there to replace each other's. They're actually going to complement each other's, help each other. Before you go, before you actually develop a model and then do the wind tunnel test, you can do a lot of CFD simulations in order to find the best model possible, best design possible for a aeroplane. And then you can put such small model of an aeroplane inside wind tunnel because it's very costly. And that is the reason that they go hand in hand in order to find out fault and many other things. So equation based simulations is one thing, which is all of all these categories, and there is agent based model where the scientific input is not that much, but it is more of probabilities, how different multiple molecules, multiple human being, multiple cars in a traffic situations are interacting with each others, how the bottleneck is getting created. Traffic simulations of a big city is one such problem, which is agent based type of simulations. There is multi-scale simulations. I was talking about docking of a protein molecule inside another bioorganisms, which is normally called as a MD simulations, molecular dynamic simulations. So this is humongous, even though it is a very small molecule, but to compute these real world phenomena, even the biggest supercomputer will fall short, and that is why we do a lot of approximations. So in summary, we are now closing up onto the computer scientific simulations part of it. So in summary, the simulations technique and methodologies requires huge compute power. I hope that we are able to come up onto the same platform of understanding on that particular part. You may ask that why cloud systems are not sufficient enough. Well, cloud is coming up. Cloud systems are becoming one of the prominent candidate for scientific simulations. A lot of people are utilizing them, but again, the performance is one issue, and that is why we do prefer bare metal performance aspect. Also, recent time you have seen that I'll be talking a little bit about it. Recent time you have seen lot of different kind of architectures, computer architectures coming up. Initially, there was single core architecture, quite a standard x86 based von Neumann Intel Pentium processors architectures. It became a de facto from 1996 to 2006, let's say, around that time. And then suddenly, from 2006 onward, a lot of different architectures started coming in. FPGA came, graphics processor came, Intel mic, Intel many core processors came, and right now you have so many other type of processors because of the AI compute need. So for specifically AI compute needs, you have many other different kind of a processor, including GPUs. The Cerebras is one kind of, Sambanova is another kind of. We call them network processor, and they are humongous, all but they are very very powerful, and they are actually enabling like Google TPU as well. They are actually enabling AI related computations, making it possible on compute platform. So rapid compute architecture oriented innovations are happening around. That is also fueling the performance gain for many applications. We are able to realize and we are able to go beyond certain level of calculations. We are very thankful that AI is the latest entry into HPC, and on national supercomputing missions, there are a lot of AI oriented calculations happening day and night on the systems. What you are looking at is a real life simulations. It's a project where we are simulating Mahanadi Basin. It's actually entrusted by government of India to Odisha government. The Mahanadi Basin is a very much flood prone, and what they wanted to do during the rainy season, every day they want to simulate that if some barrage, let's say Naraj barrage and Mahanadi barrage, there are two, here one and there one. If water is released today because of heavy rain or for any other reason, what is going to be the inundations or the penetrations of flood water inside different district and their areas. So this is what the simulations talks about. This is also a kind of fluid dynamic simulations, but it is in 2D nature. It is not in 3D natures. So on a plane maze, which is represented in the whole geographic area. So on that plane maze, how the water is flowing, we are not much concerned about the depth of the water initially. We are basically trying to find out how much water is going to be floating around to the inner areas of a particular region. So that is why 2D simulations is good enough for us, but yes, there are 3D models also, and you could see that this particular simulations, and again, this is just a representation. The actual simulations initially was taking almost 15 hours, the whole area, and our team put effort in order to optimize these calculations, and we have brought up down to 4 hours. The calculation starts around night 2 o'clock, it ends 6 o'clock around, and then the data will be processed, and there is a pipeline protocol setup. The data will be immediately forecasted to Odisha government and the decision makers, related decision makers. They will take corrective actions after visualizations. All things are placed, and our team, with support of government organizations, trying to take these particular flood simulations applications across India. This is one of the success stories under NSN, and here is much more detailed representations of the whole simulations. So the whole geographic area, as I was telling, is represented through maze, triangular maze, and the application's name is Anuga. So it is developed by Australian National University Professor Steve, and he has developed it for two purposes. One is flood simulations, another purpose is tsunami simulations, and the model Anuga, it works for both. What it simply does is how the water inflow into a singular triangle inside the mesh, how much force it is there, and how, because of orientations of the land, how it is going out. That is called inflow and outflow pressures. This is the calculations happens around, and it's a very simplistic representations of the whole software. You can go through the papers as well, the Anuga papers, and these calculations, because of these calculations, we would be able to simulate the flood. That is that simplistic way of doing it. Okay, am I taking too much of time? Okay, I think we are on time. So is there any questions till now?
So this session is still 7:30.
Yeah. So my sessions is basically it's a continuous till 9 o'clock. I'll take a
Yes,
break
sir.
in
Yes, sir. Two
7:30.
consecutive sessions you are
Right,
having.
right.
Yes, sir.
Any questions till now?
Participants, if you are having any query, question, sir is there.
Okay, no problem. I'll move forward.
Okay.
In case of weather forecasting, what they simply does is they decompose the domain. We call it a domain, which is basically a three-dimensional area, into smaller blocks, and each of the blocks is basically collections of lot of data: air density, temperature, air pressures, etc., and they are represented as a dot. Okay, this is the dot. So for each of the blocks, there will be a lot of dots which are basically representing that current state of parameters. So once you represent them in two-dimensional or three-dimensional forms, it becomes matrices, and then it becomes basically a matrix calculations. There would be governing scientific formulas, but technically it's a matrix operations. So that is why we call it as a domain. Decomposition is one of the most important part of it. How you decompose the domain, and then how do you map it to different computing platforms and computing systems. Based on that, the performance will vary. Here
Sir,
I'm trying to show. Yes. Any question?
sir, probably there's a question from on.
Sir, I have a question.
Yes, please.
I want to know though, what is the aspects of heterogeneous architecture based model or system for high performance computing?
Okay. We'll be covering that. Heterogeneous computing or hybrid computing is part of
Yes,
our
sir.
sessions. We'll be talking about it.
Oh, thank you, sir.
Yeah. So right now we are simply trying to understand what is simulation, scientific simulations. Okay. So why we are trying to understand that? Because if we understand this part, you are very much confirmed, assured that scientific simulations will be requiring high performance computing system. So that is how the domain is decomposed, and then what happens is they will be given to different compute nodes. And as you understand, this is a very simplistic diagram of a HPC facilities, where there is a master node, there is a common storage, and all the networks are connected together. All right, and that is why each of the compute nodes can see the storage, which means it can retrieve the data from the storage, and that is why when it will be doing the computations for their respective domain areas, if there is there is a requirement of exchanging the data from this compute node to that compute node, which is very much essential in case of weather forecasting. So there will be a lot of exchange of data, and if that is the requirement, then what would happen is either they will transfer the data from this node to this node, or if this particular node has written the data back to the storage, the node, the other compute node, they would be also be able to look at the storage data and retrieve it from there. However, there is trade-off. Transferring some data from this node to that node through network is less costly and faster, Retrieving it from the storage is higher costlier, and then it takes a high amount of time. That is why it is actually discouraged many cases. But there are calculations, there are applications which does that. So this is what is a very simplistic form of distributed computing on a HPC platform by domain decompositions. I hope that I am making sense. Um, if not, then please interrupt me and ask me questions. Now I'm coming to other scientific models. So, like aeroplane model, here is a model of a car which is represented through maze, geometric mazes, and there are three different techniques, scientific techniques. Apart from discretizations approaches, you want to simulate how something is propagating over. Something means either heat or air or some pressure, whatever it is. So there are three different approaches. The finite difference methods are normally used for heat transfer kind of a simulations on a hard surface. Finite element methods are preferred for a non-uniform surface or non-uniform meshes, and finite volume methods are specially related to the fluid dynamics. We want to simulate fluids, some form of fluid. So discretizations is one of the fundamental aspect in every cases. What we simply do, the governing rule is some form of PDEs, Partial differential equations, which is representing how some state of an object is moving from one stage to another stage. Now, if you want to do the calculations, you would go for variational calculations, some form of integrations, and those integrations would basically be represented on computer in some form of linear equations. So once it is represented as a linear equations, it's basically matrix operations, and then you would be able to do that. And this particular pipeline would repeat for each of the cells we call the mesh block, each of the mesh block, and then it will continue over time. So time is a vertical, it will continue over time. Here another example of a discretizations. Suppose you have created a source of a heat here on this block, and this is uniform mesh, and then you want to understand how the heat will be transferred. Okay, and heat will be transferred. This is material simulations. In case of material simulations, a lot of such simulations, material discovery, lot of such simulations are taken over. So what will happen if you generate a heat here on this particular point? It will start to dissipate to other side by blocks areas here, which is represented by side by blocks. And however, the total heat generated will remain always zero if you calculate. That means this generated heat and the transferred form of heat total, if you minus one from the another, they will always remain zero. This is the guiding principle, that initially will start from here, and then heat will start dissipating to us other side by mesh areas, and then state wise over the time how it is the heat is propagating, that you can simulate. As I said, so you have a finite difference method where we basically differentiations is the basic guiding principles. You will be doing you will be taking some form of integrations, variational methods in order to do the calculations. The much better approach is the linear approach, linear calculations approach. So the integrations methods would be represented in form of linear equations. The all things here is basically related to that. Whether you call it as astrophysics simulations, whether it is you call it weather simulations, or heat transfer model of Earth, planet Earth, seismology, which is a domain. So all those things and simulations are part of scientific simulations. And there is a finite element method, as I was talking about. You will have non-uniform meshes. At some sections, you will have a very smaller triangles, triangles, Whereas on the areas where you are not so much interested to know the result, you will have bigger triangles. You want to simulate these sections, it's much a deeper form, coarse form, and here you want to have bigger triangles because you don't want to simulate, you don't want to do that much of intense simulations for these regions. So finite element method is one very effective there. This also is done for material simulations and all. So I'll be going through some of such areas. And then there is a finite volume methods. There is a software package called OpenFOAM, which is basically falls into the domain of computational fluid dynamics (CFD), and they are all based on finite volume methods. They have a lot of other advanced variations of methods, but the guiding principles and methods is finite volume methods, where you are fundamentally looking forward to simulate a fluid. Okay, so this is what I have given a brief overview of scientific simulations. There are so many other type of scientific simulations around. I won't be able to go through all that and it would become very boring. Now we would quickly jump onto how HPC slowly evolved into the historical perspective of it. Before that, quickly, if you have any questions, let me know.
I think there is one participant was there are two participants who have raised their hands, so we are making them.
Yeah, please.
Suman, I
Sir,
think you
I
are
have a
having some question. Yes.
yes, madam. I have a question regarding the non-uniform based system. I think that I have done a little bit work on non-uniform, but it is very challenging to overcome the uh, fault tolerant technique to communication from one node to another node. So how will I overcome from this challenge?
Okay. Now we're talking on the technical terms, fault tolerance of communications or distributing the task onto
Yes,
different compute unit. That is what you are saying, right?
yes, sir.
So what I suggest, you don't do it by yourself. Okay, if you are a researcher, if you want to if you are developing a new fault tolerant technique, then you go for it. But if you are actually trying to develop or trying to simulate something, don't get into the computer science part of it, because you want to simulate something. When you say fault tolerant, you are basically telling that it is failing, you are not able to smoothly communicate or something. And that is why I will be giving lot of references to computer software. They are very much fault tolerant. They have been there, they are the de facto standard of calculations for distributed computing, so you can
Thank
use
you.
them.
Yeah, thank
You
you,
can
sir.
use
Thank you.
them. So you don't have to deal with how my one process is connected through socket communications to another node, whether they are able to transfer the network packets properly or not. All those things, challenges, are old age challenges. There a lot of abstract
Yes,
software
sir.
has been developed. I'm going to talk about them. Any other question?
Sir, I have done little bit work in open source book sim and noxim simulator
Okay.
on the platform of Unix. Uh,
Okay.
that's
Okay.
why,
Good.
sir.
Good. Yeah, you may correlate. You may correlate very easily then. Any other
Thank you, sir.
question?
So we have another query from Umar Farooq.
Okay. Yes, Umar Farooqji.
Umar Farooq, sir, please ask your query to sir. Umar Farooq, sir, please unmute yourself.
Hello.
Yes, please.
Yeah. Just now you have introduced about this quantum computing,
Okay.
and like my understanding is that the discretization of the mathematical representation kind of thing won't be there, so that you will be able to get the most exact solutions.
Yes.
But
Yes.
as and when the data is in discrete format, that means whatever the data that we are using for simulations or evaluating that, is it in when it is in discrete format, like how it will be able to overcome that?
That's a fantastic question, sir. Thanks for asking, because I'm also co-PI of one of the quantum simulation projects, so I know a little bit of it, so I'd be able to answer your questions in detail. See, not everything can be simulated on quantum systems. We are looking into the very core part of it. There is something called DFT, density functional theory. Okay, what it does, density functional theory is a discrete mechanism to tell that how the energy state of an organization, of a system, is moving from one stage to another. Basically, the whole universe is trying to minimize the utilizations of power. It is trying to reach to the ground state. You know, in quantum systems, that is the purpose of the universe itself. So all the molecules are also trying to do so. So in quantum systems, we will be giving the data in discrete form as an input. Okay. Now that input will be converted, that discrete input, which is in digital form, will be converted into analog signals. And then those analog signals will be reaching out to the quantum processor to manipulate some qubit. Now try to understand. I have data in matrix form, which computations people would understand, matrix form, 0 and 1 bit. Now I want some search to happen. I want to find out a database search, suppose where the data is. So I have to somehow represent the whole problem in the form of quantum circuit, which simply means that I have to somehow represent these real world phenomena through discrete methods, and then from discrete methods to the quantum circuit methods. Once you represent something in quantum circuits methods and search, it's called, then those quantum circuit can be given to the quantum systems. Quantum systems will simply tell, okay, here is the circuit state. After you pass it through me, here is the next state. It is not going to give you something as solutions. Now, once you have the next state, which quantum processor has told you, this is the intermediary output. You have to read out. You have to read those output using analog methods, which is basically signal processing methods, by analog methods, and then try to understand what sense they are making. Then you have to again discretize them back in the form of matrices in order to understand what actually happened. Okay, so these whole transformations, that is why in quantum simulations it is very much required that as a quantum information scientist you developed a mindset of representing a real world problem in form of digital problem, then from digital problem transfer it to in form of ansatz, which is basically a form of a quantum circuit, and then do the simulation on quantum system, then take it back, the final out, take it back, discretize it, realize the result. So there is, so in direct sentence, in very simple form, discretization is necessary. It will remain important even quantum system comes.
Yeah,
Hopefully I'm able
understood, sir.
to,
Yeah,
yeah,
understood, sir. Thank
hopefully
you.
I'm able to answer your queries. So if the, by the way, the participants, if you want to ask queries, instead of waiting for your turn, you can post the message to your channels or possibly into the chat box of this meeting link, and we can take up them one after another later point of time. That will save some time. Okay, if there is no more questions, I'm going ahead to the next part of my presentation. Now, by this time, we have understood what scientific simulations is, and we have also understood, if not for the first time, we have also understood that you require high performance computing system. You require supercomputers in order to realize a lot of things. Suppose you want to discover a new medicine, you have no other way. Before going to a real wet lab experimentations, you have to do the dry lab experimentations, which is scientific simulations. So everything, frankly speaking, everything is happening around on HPC platforms. We simply don't know. That's maybe one of our limitations, thought limitations. By the way, so if we agree on that part, that yes, for scientific simulations, we require HPC. So let's jump into HPC. I'll give you the historical perspective first, and then we'll delve down into the component-wise understanding. What are the different type of component, how they are organized, and then I'll be talking about where the performance is coming from. I'll be talking a little bit about the architecture of it. All right. So let us go ahead. Cray is the company. Before that, it is a debatable thing. IBM said in 1961 they have developed the first supercomputer, but well, it's a debatable thing, by the way. Cray developed one of the first supercomputer, and you can see the picture of that supercomputer. It was based on MIPS devices. So those devices are basically some form of transmitters, and the early Param systems designed by CDAC also developed on that technology, same technology. So Cray, it was not, why I'm saying this, it is not x86 based architecture. But easily you do programs, a lot of programming you do easily, very easily on today's supercomputing platform. It was not that. It was different kind of an architecture, and the total computing power was, I suppose, somewhere it is given, I don't remember. It was nearby some gigaflop. Where it is? Here it is, 1.9 gigaflop. By the way, a gigaflop means giga floating point operations. And to give you a just simple idea, today your mobile phone has many such processors, and even the single processors, a single core of your mobile phone is much more powerful than what that supercomputer was 1964. So it is that evolution has happened. Floating point operation per second is the yardstick you need to remember in HPC in order to understand what capacity a supercomputer has. So in terms of flops, we'll be talking about. It was designed for mathematical operations, and it was also designed for space explorations, astrophysics simulations, etc. So this is one of the two of the earliest Cray supercomputers designed. Total compute capacity 1.9 gigaflop. You may laugh on it. I may laugh, but that is the situations. At this point of a time, this data is of 2018, I suppose. Yeah, 2018 most possibly, top 500. The flop capacity you see here, 93,000 teraflop. Teraflop. Okay, here it is gigaflop, but here it comes to the Sanhui Tianhu. The supercomputing system has 93,000 teraflop. Okay, so this is the compute capacity our systems has, thousands of processors and millions of cores, almost 10 million cores here. Okay, what is the compute power it is consuming, and the electric consumptions, power consumptions, kilowatt, you see here 15,000 kilowatts, which is humongous, enough to power a mid-level city. So you can understand, to power up and run a supercomputer, it is a very costly affair. This is again, we are returning back a little bit just to touch upon that many of the advanced countries are investing heavily because they understood the reason behind it. This is 2020, I suppose. Fugaku became the largest and most powerful supercomputing platform. However, the architecture was a little bit different. A64FX. And the reason I'm talking about is it's a variable vector platform. I'll be talking about what vector processors are. So these processors has a variable vector processors, some compute in it actually. Why I'm talking about it? Because those vector processors or vector coprocessors are very good at matrix operations, array operations. Okay, I'll be explaining them as well. Right now we have Param Siddhi, which stand as this data is little bit old. Top 500 2022. We stand on 63 positions worldwide. It is the most powerful AI supercomputing platform in India. It was. Right now, it has been converted into Param Siddhi PSAI Airabad. It is called Param Airabad, and the total compute AI compute power has been doubled from 210 to it is around 400 AI petaflop. When I say AI petaflop, I means to single precision computation, sometimes half precision computations, 32-bit computations, sometimes 16-bit computations, because AI computations do not require double precision 64-bit computations. That's why we are building a systems which would give 410 AI petaflop. It is a collection of NVIDIA DGX systems. Right now, I suppose the PSI has having 82 DGX systems. National language missions is using that particular systems heavily at this point of the time. So you may have heard about something called Vasini. Those models, they are the translation models to translate some of your text and voices from one Indian languages to another Indian languages. So that is based on neural network, and also earlier days of traditional language translation methods. Those models are based at. So those models are right now getting trained, retrained, and also the service are provided on Param Siddhi platform. If I look at on the journey of Param series, we started with Param 8000. Here you can see 1991, and Dr. Vijay Bhatkar was the father of Param series of supercomputing. I started my journey with these systems when I joined 2006. It was almost about to decommission Param 10,000. So after that, in 2002, Param Padma came, and then Param Yuva 2008. On all these systems I have worked upon, and right now we are moving towards NSM systems, Param Siddhi systems, etc. I was talking about that a different country has different priorities. This is because of the cost factor and many other factors. Some of the countries are looking for supremacies. They want to be superpowers in different domain. And some of the countries like India, they are trying to be self-sufficient first, and then they wanted to develop, generate employment, and they also wants to ensure that if some technologies are being deployed, if some money has been spent behind some mission, national mission, they should have social impact. So that is why for national supercomputing missions, there was 4 vertical generation, design and development of a hardware, but also human resource development was one of the primary responsibilities.
Excuse me, sir.
Yes.
Sorry to bother you again. Sir, it's can we have a small break?
Okay. Yeah.
Then we can start take a break
I
of
think
5.
it is 7:30. So let us take a break. How many minutes you want to take a break?
Sir, it's up to you only.
Okay. All right. 5 to 7 minutes.
Okay, then it's 7:33. So we'll start at 7:40 then, sir.
7:40 exactly.
Okay, so dear participants, we are taking a small break of 5 to 7 minutes, and we'll start sharp at 7:40. So you may stay here and join at, or you can join at 7:40. Okay, I think Umar Farooq is having a query.
Yes, please.
Mm,
Can somebody read out?
Yes. Yeah, no, he has. Yes,
Yeah, good
Umar.
evening, ma'am. Ma'am, it is not a query. Actually, chat is disabled. Can you enable chat so that we will be able to post any message?
Actually, the problem is when we are making you people as attendee, then automatically the chat is getting disabled. Right, Kamalesh sir?
Okay, ma'am. Next thing, are you sharing this recordings, ma'am? Is it possible?
Yeah, we will be sharing
Yeah,
and we'll be
thank you.
sharing the YouTube links as well. And sir will share his presentation. Once we get it, we'll definitely share with you all.
Yeah, thank you.
Yes.
Okay, so participants, we're taking a 5 minutes break and then we'll be joining. Thank you.
Thank you. Thank you.